let's keep going and talk more about continuous functions. So in my previous lecture on this subject, we talked about continuous functions are functions that play very nicely with limits. And we found some formulas for building more complicated continuous functions out of the more elementary functions that we already know about, like polynomials, square roots, trig functions. There is a technical point that I need to cover. In the same way that we have one-sided limits for piecewise functions, we're going to have one-sided continuity for piecewise functions as well. Now, when I have just a single formula, it makes a little bit more sense to just talk about continuity, to just talk about limits and not worry about left-sidedness and right-sidedness. But it is a detail that's going to be important towards the end of this course. So I'm going to talk about it now and do a refresher on this material when we get to things like bounds of integration. That's a far ways away though. For continuity, this definition should look very similar to the left side limits and the right side limits. In fact, they're kind of baked into my formula here. A function is continuous from the left at some coordinate x equals a if the left-sided limit as x approaches a of that function f of x is equal to f of a. So just like continuous functions have limit as x approaches a of the function f is equal to the evaluation of that function at coordinate a, I can do the same trick with a limit coming in from the left. I call that left-sided continuity or left-hand continuity at the point A. Now, if we can do left side, we can do right side as well. And that's just saying that if the limit coming in from the right of the coordinate x equals a is equal to the evaluation of the function f at a, we'll call that right-hand continuity or right-side continuity, or the function is continuous from the right. Now again, these ideas make the most sense for piecewise defined functions. Here is a piecewise defined function. I'm splitting my formula at the coordinate x equals 0, and if I'm to the left of x equals 0, I use the formula 2 times x. For x equals 0 and above, I use the formula e to the power x. And just by looking at this formula, I can see which side is going to be continuous. Do you think it's going to be left-hand continuous or right-hand continuous? So the side that has the equal sign on it will be the side that has continuity. Now again, that's only as long as the formula there is also continuous. So I got to check, is e to the power x a continuous function? Yes, it is. Let me show this on a graph instead. So here I have graphed my function. This is just the way I would write it in Desmos notation. And Desmos is a little persnickety in that it has not drawn the very nice empty dot and filled in dot. So my formula says if x equals 0, I am supposed to use the formula e to the power x. So I should have a filled in dot here at x equals 0, y equals 1. And I should have the empty dot down here at x equals 0, y equals 0. However, I can just see from this graph that the function is discontinuous. And if I trace my finger from the right, if I trace my mouse from the right, I come to the coordinates 0, 1, which is the value of the function, right? Y equals 1 when x equals 0. So there is my right side continuity, or my continuity from the right. From the left, I would say that this function is not continuous from the left. So altogether, right, I've got a discontinuity here. I could drive a truck through that if I just zoom in a little bit more. But I do have continuity coming in from the right here.